Hello, everyone. Welcome back. Our next speaker is Ningchuan Zhang from University of Pennsylvania. He will give the last two talks on chromatic homotopy theory. Today, he will talk about Bousfield localizations. Welcome.
Thanks, Rindra. Thanks for the invitation and the introduction. So today I will talk about the 12th lecture in chromatic homotopy theory on Bousfield localization. And I have posted the links to the 3 references I wrote here. I don't know if everyone can access them. So even though this topic is listed as part of the chromatic series, it's also pretty categorical. It's pretty categorical. It will lay the foundation for the next talk on monochromatic layers and chromatic convergence. But I would say the first half or most of this talk will be pretty categorical. Okay, so let's get started. So what's the motivation for Bousfield localization? Well, some motivation, it's not historical motivation, but what I think should be is happening. So first part, we'll talk about E-acyclic and E-local spectra. But before that, some motivation. Sorry, let me get started. So E-acyclic. So in the first part, we'll introduce the notion of E-acyclic and local spectra for a homology theory. And so one motivation is in algebraic topology or in homotopy theory, we want to classify objects like spaces, spectra, right? So ideally, we want to classify, say, spaces. Well, what do you mean by classify? Well, ideally, the best case scenario up to homeomorphism, but that's too strong. I can see in algebraic topology, we usually in homotopy theory, we usually want to up to homotopy. But if you want to classify things up to homotopy, then two things are equivalent. To a homotopy equivalent, usually you have to construct explicit map homotopy equivalences and the explicit isomorphisms, explicit homotopy equivalences between those maps. So it's complicated. It's not always so easy to do so. So usually we already don't. So usually there's a weaker notion or weak equivalences. That with this term we have heard a lot in the lectures. So what do we mean by weak equivalences? So recall a map f from x to y is a weak equivalence if f star is an isomorphism on stable on homotopy groups, or in this, since we're doing stable homotopy series, so let me just say it's just stable homotopy groups. Now, isos for all n. If you are doing just unstable, then probably for pi 0, you have to say it's a bijection of sets because a priori. And then for higher homotopy, because you have to say for every base point, this is an iso, things like that. So, and we know weak equivalences are not homotopy equivalences. There are counterexamples, but for certain type of spaces, they are equivalent. So you can see here, weak equivalences are some sort of equivalence relation. The equivalences detected by stable homotopy groups. By name just the homotopy group, so it will be a little by homotopy groups. But homotopy groups, well, one observation is stable homotopy group is a generalized homology theory. Represented by the sphere spectrum. So you may wonder, what about other generalized homology theory? And especially because we know stable homotopy groups are hard to compute. So, well, if you hand me a map, you want to ask if there's a weak equivalence, it might not be so easy to check. Just say, let's compute the homotopy groups. It might not be so easy. So maybe we want some weaker, even weaker notion, like we want to now. So the natural question is, what if we replace the sphere spectrum or stable homotopy groups by some generalized homology series? What kind of generalized homology series detect? To what extent can we tell two spaces apart through a generalized homology series? And that leads us to this leads to the following definition. Let E be a generalized homology series. Then a spectrum AX is called E acyclic if the E homology of X are all trivial, or equivalently, this is also equivalent to say E smash with X is contractible, weakly contractible. Okay. Second, X, also a spectrum, is called E local if there's no map from an E acyclic spectrum. So if for every T E acyclic, the mapping, the homotopy classes, there's only a trivial map from T to X. And finally, a map of spectra F from X to Y is called E equivalence if I should use a different color, sorry. It's called the E equivalence if if F star on E homology groups is an isomorphism. In terms of spectrums, is also equivalent to say that if you consider the induced map F, one smash F that goes from E smash X to E smash Y is a weak equivalence. This is the weak equivalence. So okay, so those are some examples. I need to do two things now. One is to justify, like we have this notion of local is sort of, people, you probably have heard of it in classical community algebra. So you must, well, what's the relation? And also what does acyclic mean? Another thing I want to do now is to give you some examples. So maybe let me first give you some examples. Some examples that everyone has computed before. Example. The first example I want to give is the ordinary homology group with Z coefficients is still a generalized homology series. So let's say E is HZ, and then I claim any then X is E acyclic if the E homology of X is trivial. Well, there are such spaces. Actually, not spaces, spectra. Some examples include something you have heard many times in recent lectures. So e.g., X is the Morava K-theory. Of course, this is not so trivial, so easy to say that. This is not so easy to say. And we also have any. And what about examples of local spectrum? Well, any Allenberg-McLean spectrum. HA is local. Why? Proof. Actually, the proof is basically follows directly from the universal coefficient theorem. So recall that, say, suppose T is cyclic. Suppose T suppose the T if T is a cyclic, then we have T to HA. This is the zeroth cohomology of T, ordinary cohomology of T with coefficients in A. And this is 0 by universal coefficient theory. So for any element, so if you take E to be HZ, then any Allenberg-McLean spectrum will be local. How about I take E to be HQ, the rational Allenberg-McLean spectrum? Then I can give you some examples of cyclic. Then I guess we have all computed the cohomology groups of things like the projective spaces, the real projective spaces. Then we know RP2 is cyclic because it's rational cohomology. So here, when I say E star, implicitly, I'm using reduced cohomology. I'm doing reduced cohomology everywhere. RP2 is cyclic because, if you remember, the reduced cohomology of RP2, cohomology doesn't really matter. With rational coefficients, it's gonna be 0. So more generally, you can say any Moore spectrum or Moore space, Moore spectrum for a finite group where A is finite group is cyclic. So you can see here, we basically, for if you take E to be Allenberg-McLean spectrum and verifying whether the spectrum is cyclic or local, a lot of times it really relies on this computation of ordinary cohomology and the universal coefficient theory. You can see that. Now let me justify. Let me make an analogy with classical algebraic commutative algebra. So analogy with commutative algebra. By commutative algebra, it really means the classical one-categorical commutative algebra. So let's say let R be a commutative algebra, N be an R module, F be some element in R. Then we know that M is F torsion. This is if and only if if the multiplication by F map is 0, right? But there's another way to write it. This is equivalent to say the base change of M from R to R1 over F is 0, is a 0 motion. So in this sense, you can kind of say this torsion. So you can kind of say M is, in the language of this local, cyclical local, this really says that M is sort of, now you can kind of say M is R1 over F cyclic. See that? So this acyclic sort of corresponds to torsion, sort of. How about the other one? If for any F torsion module M prime, the Hom set or Hom module from M prime to M is 0, will be 0 if suppose then this one necessary condition at least. The necessary condition is F, the action of F on M is invertible. It's an isomorphism, so, or it's an iso. Just say it's an iso. So you can kind of say in some language you can say this M is sort of F local. M is F local. So in this sense, this local spectrum, E localness sort of corresponds to this localness in terms of homology theory. Okay. Well, now I'm gonna give you a very useful criterion, NAMA. Equivalence description for E equivalences. No, for E localness. A spectrum X is E local if for all E equivalence, for any E equivalence, F from X from Y1 to Y2, the mapping induced map on mapping spectrum. So it will go backwards, Y2 X to Y1 X. So let me call this, I don't know what's the best way to call this, maybe upper star. This is a equivalence. Is an equivalence. How can we say this? Well, proof. The proof is pretty straightforward. So if F from Y1 to Y2 is E equivalence, then we can take its fiber or co-fiber. I mean, either way would work. Then this implies the co-fiber of F is gonna be E acyclic. Right? You just do the non-exact sequence of E homology. I mean, E is a generalized homology series, so it has satisfied those axioms, and so you will have a non-exact sequence for co-fiber sequences. And now we just map this co-fiber sequence Y1 to Y2 to this co-fiber of F into X. Then we'll have what? Then this is we'll have this flips order. Map co-fiber of F X to map Y2 X to map Y1 X. So, well, actually, I think this is if and only if I'm not wrong. I think this is if and only if. Yeah. So on one hand, if X is E local, then the fiber this term will be contractible. And this is contractible. So that means, which implies F star is an equivalence. Is an equivalence. And on the other hand, other direction, on the other hand, I mean, any E acyclic spectrum can be realized as a fiber of E equivalences. So any E acyclics can be realized as a co-fiber. of equivalence map, equivalence. So this proves, this implies the other direction. Okay, so that's the first part of my talk of this lecture. We have introduced the notion of E-acyclic, E-local, and E-equivalences. In the next part, we'll start to talk about Bousfield localization. Any questions? Question in the chat? Okay, it's in front in the chat. Okay, nice. So next part 2, Bousfield localization. In short, what does Bousfield localization do? So slogan. Let E be a spectrum, be a generalized homology theory or spectrum, be a homology theory. And LE and X be a spectrum. Then we'll construct, then we want to say the Bousfield localization. This map is the best approximation of X by, of course, I have to do quotation, by E-local spectrum. What do we mean by that? So we can formalize this idea to say that we can formalize this idea is to say that a Bousfield localization, the Bousfield localization, so we can now define more precisely. LE, this is a functor from spectrum to itself, idempotent functor. I don't know if idempotent is part of the data or you can deduce it from the other properties. Together with the natural transformation from the identity functor, with the natural transformation eta from ID to LE, such that for any X, for any spectrum, eta from X to LEX is an E equivalence, such that this is an E equivalence, and LEX is E-local. So by best approximation, I really mean we want to replace X by an E equivalence. We want to replace X by a E-local spectrum. We are an E equivalence. So for folks well versed in model category, this sounds a lot like a vibrant replacement. And yes, that's precisely the construction of Bousfield localization. So, so the first question, so the construction, so theorem by Bousfield is such functor, LE, this pair, LE, comma, eta, they exist. We can construct it, and the construction, maybe let me just say idea of the construction. So since I say it exists, so I better give you a construction. Idea of construction is, so in spectra, so we have been talking about infinity category a lot this whole in this whole summer school. There's also a related notion called model category, and the category infinity categorical spectra has a model category structure, a UL model category structure, where the equivalences are are just the real weak equivalences of spectrum, and fibration and co-fibration are the real ones. So now we can replace, if we replace weak equivalences by E equivalences and keep co-fibrations and keep co-fibrations. Then, if you know some model category theory, you will know fibrations are so-called determined by the lifting properties. So they are the so-called right complement of trivial co-fibrations. Trivial co-fibrations. So sort of a right complement. I think this is a notion I learned from my professor in grad school, Professor Charles Rask. Like this notation basically is sort of a lifting diagram, which I will draw in a moment. And in this case, since we have we keep the co-fibration, but we have replaced weak equivalences, so it's gonna be a co-fibration such that it's an E equivalence. Such that it's an E equivalence. So now, under this setup, in the new model category, in the new model structure, this E, let me call it the E model structure to make a distinction. In the E model structure, the projection map, the collapsing map from X to a point is no longer, it's not necessarily a fibration. So using the general machinery in model categories, then we have a factorization. Then we have a factorization. We have a fibrant. There's a factorization. Let me just call this X prime for now. So there is a factorization. Then there is then there is a factorization. X to, let me just call it L, it is. Such as the first map is a weak equivalence in the new category. So this is a weak equivalence, the E equivalence. And this will be a fibrant, like a fibration, a new fibration. So maybe let me call it E fibration. And actually, I claim that this map being E fibration, if you check the condition, so since this is E fibration, i.e., we have a lifting for any map for any F from Y1 to Y2, that's an E equivalence. And simultaneously E cofibration, but E cofibration is just the real cofibration. We'll have a lifting diagram and maps like this. We'll have, there's always gonna be a lift. And this is precisely, then this is precisely what we just covered in the number. It's precisely the number we mentioned. Namely, a spectrum is E. This is precisely the number, i.e., like a spectrum, i.e., LE is E local if such lift always exists. Such diagram always eliminates lift. Means a lift. But if you really want to know how this factorization thing goes, that's a big rabbit hole. It uses a small object argument, and yeah, if you want to know that, I probably have to read some model, some reference, some books or references on model categories to really figure out how this factorization in model category works. Okay. So let's just assume it exists. And now we'll give you two universal properties. Of a localization. It's actually both initial and terminal in certain sense. This is initial is initial among maps from X to an E-local target. To an E-local target. And it's also terminal among maps among E-equivalences, starting among E-equivalences from X. So I'll give you one proof and the other is entirely similar. So maybe name it to your first proof. So suppose X to Y, we want to show the following. We want to show that, yeah, we want to show, so suppose X to Y, what's the right direction? I think yeah, this one is probably better. X to Y is Y is E-local. This is, wait a sec. So suppose F from X to Y and Y is E-local. Then we consider we consider the map from X, localization map from X to LEX and its fiber. Well, by definition, this fiber is E-acyclic. So that means the composition of the map from the fiber of the localization map to Y, this composition has to be 0. This is 0. This composition is 0. And by the universal property of co-fiber, since we're doing things stably, fiber sequence is also co-fiber sequence. So there exists a map. There exists a map. So that's how you prove that this localization map is initial among maps from X to an E-local target. Just play around with co-fiber sequences. And the other proof, the other one is entirely simple. I need to maybe speed up a little bit. So another important property is if E is so-called, there are many names for this kind of object, is a weak ring spectrum. By weak ring, and sometimes it's called mu spectrum because people don't want to say it's a ring, i.e. Spectrum, E has E plus, it has a multiplication, so-called multiplication, because we only require the minimum information on this multiplication. It has a multiplication, it has a unit map. Let me call this unit map also, let me call it by epsilon, because why not? Such that the composition from such that the composition E to S naught E to E smash to E smash E to E smash E by epsilon smash 1 and by mu. This is ID. Then any E module, I also need to get quotation mark because this is not really a module, and is E-acyclic, is E-local. Of course, if your E is very nice, like E infinity ring spectrum, and F is the honest E module, like for this E infinity ring spectrum, then of course this also holds. But for this first statement, we'll actually only need the minimum information for this to hold. And now maybe let me tell you what E module means in this case. In this F, that is M plus an action from that is unitary. I.e., if you consider the map M to E smash N by epsilon smash 1 and by alpha, this is the ID. So it's like we are only doing like ring and module, but we only require minimum, like it is unitary. We don't even require associativity or anything. So some people, I guess, are very reluctant to call this a ring spectrum. They call it even just a mu spectrum. But this is already enough information to show that this M is illocal. And the proof is not too bad. Let me just, I think I have several things I want to say, so let me just give the proof. The proof is very straightforward. Okay. So given a functor, this localization functor, one thing that we care about is that those functor preserve limits, co-limits, right? Well, it does not preserve, usually the localization functor does not preserve limits, not co-limits, but it has some interesting interactions. So next, homotopy retracts and the limits of E-local spectra are still E-local. Let me do the there's a question? No question. So let me do the retract. So for the retract, say if X is E-local and Y is a retract, so that means we have the other direction. So you have Y to X to Y. This is I, R, and you have a map. You have this is the ID map on Y. And now, if you you just map this entire composition. Oh, sorry, it's the other way. You just for any cyclic spectrum T, we have that the mapping, then we consider the mapping spectrum from T to Y, and then you can do R star to map from T to X, then to I star back to map T to Y, and the composition is the identity star. So this is ID, but this is 0 because X is illocal. And this proves that Y is also illocal. For homotopy limit, the proof of that uses is basically the universal property of homotopy limits. But a caution, even though homotopy limits of E-local spectra are still E-local, this does not mean that LE does not necessarily does not preserve homotopy limits in general. Even though homotopy limits are sort of E-local spectra are close under homotopy limit, but this doesn't mean localization. This functor itself preserves homotopy limits. Okay, so that's for the limits. How about co-limits? For co-limits, so let E. Oh, I have skipped the important notation definition. Let SP sub E be the full subcategory of local spectrum. I have skipped this very important definition, sorry. And with this, I can describe how localization functor interacts with colimits. So let E be a spectrum, and this is a spectrum. Then the following are equivalent. So first, this inclusion, this full subcategory is closed under colimits, homotopy colimits. Of course, by this we mean if you take a homotopy limit in the category spectra of E local spectra, then it is E local. That's not always calculated actually. Second, localization functor from spectra to itself, it preserves colimits. And third one, this is the most important one. If this says that the localization of a spectrum amounts to a smash product. So what smash product? You just smash it with this localization of this first spectrum. So this proof you can find in Norris notes. This proof you can find in Norris notes. And if X satisfy if E, if the above, I mean the equivalence. If the above is satisfied, we call the localization functor smashing. And we'll see very quick. We'll see in the next part, in the next section, that there are localization functors which are not smashing. And so there, the proof. I think the proof is basically by universal properties of structure. Do I have time to go through any of the proofs? Maybe. Okay, let me. Yeah. So the proof is like this. We prove that 1 implies 2, 2 implies 1, and 2 is equivalent to 3. For 2 is equivalent to 3, this uses the fact that any colimit preserving functor F from spectrum to itself is of the form F of X is equivalent to X smash some spectrum T. So this is a pretty strong characterization of all colimit preserving no functors of spectra. I mean, it has to be smashing in this sense. And so what is T? Well, since the sphere spectrum is the monoidal unit, then we have LE. If LE is smashing, if LE preserves colimits, then we have LE of X is equivalent to X smashed with some spectrum T, and now we just take X. Well, what is T? T is just the localization of the sphere spectrum. And conversely, if your localization functor is given by smashing with some spectrum, of course, it preserves all colimits. The other direction is easy. And for the first two implication between 1 and 2, that uses the universal properties of localization and the homotopy colimits. So I will just leave that as an exercise. Or you can find it, I think, it's in Norris notes. Okay, so I think we have talked about a lot of properties of the localization functor, but we haven't, except for the animal McLean spectrum, we haven't seen much concrete examples yet. So in the next part, we'll do examples. We'll give you explicit formulas of Bousfield localizations with respect to certain homology theory. But before we give you example, I want to first give you an important theorem and some construction that's needed to state those explicit formulas for Bousfield localization. So the first theorem, so actually we're gonna localize with respect to Moore spectrum. So for that, we need to use the universal coefficient theorem for stable homotopy groups. This is the following. If X is a spectrum, A is a abelian group, MA is a Moore spectrum for A. Then there exists a natural shortly that sequence of the following. So you want to compute homotopy groups of X matched with the Moore spectrum. In the literature, this is also usually denoted by called homotopy groups with coefficients in A. I guess maybe the reason is it behaves like, yes, it's like if you think about homotopy groups as a generalized homology theory, then it's sort of like as with coefficient because it also has a universal coefficient. So universal coefficient says it has a Schrodinger sequence where the kernel part is just pi n of X tensor over Z with A, and the co-kernel part is a Tor term. A with pi n minus 1 of X. And one caution, one warning, this does not necessarily split. Unlike the universal coefficient theorem for homology, this does not necessarily split. That does not always split. One example, yeah, there are explicit examples. We'll use this universal coefficient theorem later. And now let's give some definition. I think we may have seen this kind of construction already. Like I think in Weinan and Weinan's talk and in Vital's talk, probably we have seen this mapping telescope. How can we invert an element in homotopy group? So let X be a spectrum. And we fix F be in some pi k of the endomorphism mass space of endomorphisms from X to X. First, we can try to invert F. This is the homotopy colimit of the mapping telescope. So what do I mean by mapping telescope? So this F is a map from Sk to the X to X, and using a junction, we can think of F as a map from X to the suspension K of X, can identify using a junction. Then we just compose it, iterate, just compose it. And this is the suspension KF. And if you take the homotopy colimit, we call this inverting X1 over F. This is like classic combinatorial algebra. If you want to invert an element in a ring, you can also do use this formula to come to realize this inverting an element as a colimit. So one special case is, well, there's always pi 0 of S naught, which is a Z. This we always have a map into pi 0 of any endomorphism of X of any spectrum. So in this case, if we want to invert, say let S be a multiplicative subset of, say, pi naught S naught. Actually, I think I can do more. Then pi star. Then we can define S inverse by inverting all the elements by basically adding all units such that f is in S. And in particular, if this S is a set of, if S is a set of natural numbers, that's coprime to P. Of course, N is not 0. Then we call this inversion just the P localization, just as in classical. We call this the P. We call this the P localization, just as in classical commutative algebra. And if we invert all numbers, if we invert all the natural numbers besides 0, just invert everything, then that's what we call rationalization. Maybe I should really write it the other way. Sorry. So let me just drag them to the other side. This is this is xp, and this is x cubed. And finally, we can also define completion. But before that, let's define f x over x quotient out by f to be the cofiber of. In this case, my f is different now. Somehow I decide to use this f. Somehow I decide to use this map as what I call by f. Then we can define the completion of x at f to be the homotopy limit of x quotient by over f, and it receives the map from x over f squared, so on and so forth. So with those in mind, I can now finally give you some explicit formulas. Examples. First, if our spectrum, if E is the Moore spectrum for Z1 over P, where P is a prime number, then I claim that the localization of a spectrum, in this case, it's just invert P. And in this case, it is smashing, since, I mean, in the formula, how we invert is a homotopy colimit, so it definitely preserves colimits. And by that proposition, so it has to be smashing. And that's to say this is equivalent to X smash with the P inverted sphere. And how can we see this? Proof. So we just need to show that the map, inversion map, is an E equivalence into E local spectrum. So first, notice the universal coefficient theorem and plus the fact that Z1 over P is flat over Z. This implies that for any spectrum, pi star y smashed with M 1 over P, Z1 over P. This is just pi star of y tensor with Z1 over P. So we have y is, so this basically tells you that, yes, so this basically implies that the map is indeed E equivalence. That E equivalence. And also, how do we say it's, we also need to show the target is E local, but first to we need to know what are the E acyclics. So this also tells you that Y is E acyclic if and only if the multiplication by P map on Y is 0. That's basically, remember, a while ago I was explaining to you the analogy between a cyclic and torsion, and that's basically what's happening here. So basically Y is P torsion, you can see it that way. And if Y to Y is P0, then we can say that the mapping, the homotopy classes of maps from Y to X1 over P has to be 0. Because on one hand, this multiplication by P map is 0 on Y, but it is invertible on X. So there's definitely no map between them. So that's 0, this shows. that x1 over p is indeed E-local. So following this example, we can invert more elements, and in particular, if E is the Moore spectrum for the p local integers, then LEX is just x localized, also x localized at p, this prime ideal, which is also smashing. This is also smashing with the p local sphere. And by the way, in those examples, you can say in this example, just the localization is smashing. So definitely there's no guarantee that the smashing preserves homotopy elements, especially when you are smashing with a non-finite complex. And moreover, if E is the Moore spectrum for the rational number, then LEX is the rationalization of X, which is also the smash product of X with rational sphere. In this case, this is just real E. In this case, we write LQ for this localization. Okay, I only have 4 minutes left, so let me just rush through the next example, 4. How about the localization with respect to something that's not a flat module? If you localize with respect to this finite torsion group, lemma P, then it's pretty non-trivial that you will see that in this case, the localization happens to be the P completion of X. And it's not smashing. And why do we care about those localization of those things? Because we have the Sullivan arithmetic fracture square. Sullivan arithmetic fracture square, which says for any X, for any spectrum, we have a pullback square. So X is a pullback. X has a rational localization map, as well as localization for all primes. So, actually, in this case, with this LP, in this case, this is what we call LP. This localization is what we call LP. And then both maps has a map to a localization first with respect to those LPs, then with respect to Q. And this is a pullback square. And for those of you who knows the number theory, this is very similar to, say, the pullback diagram associated to the Adele of a ring of integer of a number field. And you can kind of say we are starting to get some finer structure of a spectrum. We have now using this localization fractures, we have split up the rational part and the P complete part. In the next lecture, we'll use chromatic localization to study even finer structures of the LP localization of a spectrum. So I think that's what I want to say for this lecture. Thanks for listening.